I guess mine's my voice. Okay, we're gonna start. If I tip my head forward, you can hear me. Right, okay, we're gonna make a start because it's 7:08, so it's a good time to go. Right, hi and welcome to the March edition of the DigitalOcean Amsterdam Meetup. There's quite a few familiar faces, which is super nice to see. But for those who aren't familiar, I am David. I'm the guy who sends out all the emails. Yes, and I'm the host, so that's my job. If you haven't been to a DigitalOcean meetup before, you can expect we're a super chilled meetup. There's beers, there will be pizzas later, wine, soft drinks. Like, it's really chilled. We don't do like recruiter spiel, not corporate at all. Yeah, it's just a casual night out, which is great. There are a few things I have to mention before we start. So, like toilets, right at the back. There are guys and girls toilets, obviously. There's also fire exits, which I think I do a bit later. But anyway, they're like just over there and just where you came in. So that's great. What else we got? Yes. So we have a word from our sponsors. So obviously, DigitalOcean is providing the beers and the pizzas and all those things. And Your Majesty, which is what the office is. Yeah, they provide the office, and O'Reilly are doing the raffle prize, which is a bit later on. So we'll do that after the break. If you don't know who DigitalOcean is, they have servers and they have cables, and you pay them for their servers and their cables.
How much for the cable?
The cables come with the servers. It's a bargain. They put their beautiful software on top of these cables and servers, and this is a really terrible frame rate. But yes, they have a beautiful UI, and you can get through it with an API as well. So if you use Docker Machine, really nice. And yes, they do lots of things, and yeah, really useful. And it's a lot smoother before, but it's not very smooth there. Anyway, yes, and basically they make doing servers easy, because if you want to do it yourself, it's quite difficult, as this GIF explains.
Is this service included in the price?
Yeah, they don't pull up the plug. It's great. No. So yeah, as I said before, they do the beer, the wine, and the pizza. So there's those. Your Majesty is the office that we're in, and I work for Your Majesty. We are a bunch of creative people. There are guys and girls. Interesting fact is our dev team now has an equal amount of guys and girls. It's like 50% split, which is amazing. So, and we do, yeah, we are a creative agency. We focus mainly on web. So we do websites, web apps, production, etc. And here's a few things that we do. So we work with the Samsung, and we work with Samsung SmartThings. We make their website, which is super nice. We recently did Auto, which, if you don't know, is a car rental scheme where you share a car between like several people, and it's super cheap. It's really beautifully website. We also do Rockefeller. They do skiing, and there is a nice website for them. And more recently, we've been doing iTrack, which is we use machine learning and AI to help marketeers and designers measure visual impact of their content. So that's kind of like brand new. It's coming soon. There is a website, but there's not a lot on it. But it's brand new. It's cool. Also, O'Reilly, they make books. You may have heard of them. These guys, there are some of their books. This month they have given us some stickers. There's like tattoos over there as well, because we are cool and street. So yeah, there's instructions over there. You just you stick them on and put water on them, and you're as cool as Hugo. He's rocking one of those O'Reilly tattoos. Yeah, so that's really great. They also provided us with some books, which is great. So in a raffle after the break, we will be raffling off this machine learning book, which is cool if you want to do that kind of thing. And they also give us a discount for any of their conferences. Their conferences are really good, and you can get 20% off using this code here. So that's helpful. Let me take pictures. Great. Yeah, the agenda for tonight. I'm so glad I updated this. Yes, it's 6:30, which is when it started. So you managed to find a seat and grab a drink. This is the introduction to the meetup. Bas is doing traffic signal. He's finding all the traffic signs in the Netherlands. So I'm really hoping that'll be really interesting. There is a break in the middle, so there's a chance to get beers, drinks. I will top them up. Go for the toilet as well. Just chill for 5 minutes, and then Daniel, who is yet to turn up. On his way. Great news. Yes, he is on 8, and yeah, he's giving us a deep dive into what Picnic do with machine learning. So that will hopefully be really interesting. And then after that, 8:45ish, pizzas turn up. We have a lot of pizza, so help me eat it. And yeah, you can hang around for as long as you like. Just chill, chat. We will make some space, and yeah, lots of networking. I didn't update the slide. Okay. Well, Erica played no part in this meetup whatsoever, but Hugo played a fairly big part because he is in charge of all my live stream and technical stuff. Sharon is official wine taster of the evening, so if you're drinking wine, you have her to thank because I have no taste in wine whatsoever, so she helps me out there. And yeah, Valerie, who you hopefully saw at the start, she is in charge of making sure you have a name badge and signed you in, which is important for later, which we will explain soon. What else we got? Emergencies, right, yes. So if there is a fire, which I really hope there isn't, there is a fire exit behind you. You have to climb over maybe a plant pot and go down the stairs. Or you can go this way, no plant pot climbing, down the stairs, and we all go over to the bridge over there, chill, take your beer with you, and then we hopefully put out whatever fire it is. So hopefully it never happens. If somebody falls over and hurt themselves, we have plasters. Hugo is a certified plaster putter-runner.
Yeah.
Yeah, so that's great. So hopefully none of those will happen. We can just chill and have a nice evening, but we now know what to do. We also have a code of conduct, which is fairly serious. Yeah, DigitalOcean is dedicated to providing a harassment-free event experience for everyone, regardless of gender, gender identity, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion or lack thereof, or technology choices. It is a lot longer on the website, but the general gist is that if you are nice to other people, they'll be nice to you, and we're a nice bunch of people, so this shouldn't be hard. And yeah, just be nice to each other. If anybody isn't nice to you, you can come and find me or send me a tweet or a message, or yeah, just get in touch and I will be mean to them. So yeah, all of this is outlined in the code of conduct. Yes, the calendar is a bit bare at the moment. Yes, next month we're doing Kubernetes. We've got a good dude coming in talking about the introduction. If you're new to it, tells you how it works. And then we've got Daniel from Picnic. He's coming back to tell us how they orchestrate multi-site deployments with Kubernetes. That'd be really cool. And then in May, there's the Code Motion conference. So hopefully I can like steal someone from that. We'll do it a bit early. Normally we have it like the second or third week of the month, but if we do it like first week, we can like steal someone from the other side of the world, and that's great. But I'll keep you posted. Yes, if you have any feedback, you can always send me a tweet. Samantha is the person that runs the DigitalOcean meetups globally, so you can send her messages. She has an email, samantha@digitalocean.com. We use the DigitalOcean meetup hashtag if you want to send nice things on Twitter, and I will like them. Yeah, so if you want to do feedback, that's the way to do it. But we have something new. So I set up a DigitalOcean Slack channel because I wanted a bit more feedback from you guys as to the kind of content that we do every month, as to like what food we do. So make it more like a democracy. Yeah, if you join, this is how you join. Slack makes it really difficult to join Slack channels, but this is an easy way. Go to that link, join the chat, and yes, then you can be a part of it. Because there's like little things like people come to me and be like, oh, please give away free tickets. And I'm always a bit like, do we want to sell out a bit? So hence I will pass that on to you and you'll be like, yes, of course we want free tickets. And then we will do them. But yes, obviously it has the same things as here. So we have to be nice to each other. I am judge, jury, and executioner on there. So if you say nasty things, you get kicked off. That's just how it is. But yes, if that's something you want to be a part of, there's a link. If nobody wants to be a part of it, I will kill it. And if it turns into a monster, I will also kill it. But I thought I'd give it a go. So yeah, we'll just see how that turns out. And then that is it. Does anybody have any questions? Nobody has any questions. Right, I'm going to hand the floor over to you, sir.
Yes.
Yes.
I hope it's easy for me. Yeah.
Give us 2 seconds. Right, there's a cable. Nice. Thank you. Oh, got one. There's the microphone. Good. Right, on this.
That will be loud on Livestream.
No.
So do you want to?
Yeah.
Yeah. You are live.
Good stuff. On there. Of applause.
So the challenge we had to face, or we faced in our company, was we got a request to find every traffic sign in the Netherlands, and so this sounds sort of hard already, in my opinion, but this is actually hard, and I'm going to show you how hard. It will involve a lot of machine learning, so I hope you guys are up for that. And actually, what we see is that some of the machine learning is sort of easy, but it depends what you want to achieve with machine learning, if your problem becomes more difficult or easy. So, if you look at some of the traffic signs you see out there, they are not so inconsistent or consistent. So, this one is quite rare. So, you have a bicycle lane, where you can also have a car, a motorcycle, and a... Okay. So actually, to be honest, this is not what we are doing. We don't check the consistency of these things. We only find them. We have a partner who does this. But it was a nice example. So let me get into some introduction. So I work for Cyclomedia, which is this company logo over here. So what does Cyclomedia do? So basically we call ourselves the professional Google Maps. Basically selling selling street level imagery, selling water level imagery, and selling aerial imagery. But we sell it to companies and especially to the government. So our client base is most of the government agencies in the Netherlands, like all the small municipalities, all the big municipalities, and then we have some contracts with some of the bigger Dutch government agencies, and then we have contracts with insurance and other things. So the nice thing is we do large-scale recording of the Netherlands every year. So every year we drive the Netherlands, we drive the entire Netherlands, which is different than Google does. Google drives Amsterdam every year, but if you go to a small village, it's they drive maybe every 5 years, sort of. So it's sort of another business model. And then our recordings are very accurate. I will come back to that. And accurate means, yeah, so making an image is always accurate, you would say. We actually precisely know where this image is located in the world, and that allows us to, given that we see something in the image, we can say where it is in the real world. And that's for us very interesting. And then, of course, you can, like with Google, you can sort of see our images in a web application, and we can show you the images, stuff like that, given that you pay us, of course. So facts and figures. So we have 30 million recordings every year. So we record panoramic images, so that are sort of images where you can view like this. Very easy. We drive with 40 cars. We have very much customers, and yeah, so we have like a big website with lots of requests coming in every day. And so we don't only have customers in the Netherlands, we also have customers in Germany and the US, and actually the city of New York recently became a customer. So we have recorded the entire city of New York, and there, instead of driving every year, we drive every half year. And so we are getting bigger and bigger also in foreign countries. And yeah, our main foreign focus markets are now Germany and the US. I'm more for the technical side of the company, and the company has actually 5 technical parts. So the first one is the car. So we have our own sort of camera on the car. It's all very specialized. I have no clue about hardware, but this allows us to make very good recordings, or they tell me. The second thing is, then given that we make a recording, we need to position it exactly in the world. So we have a second group who is sort of doing all this. Given your image, how can I sort of put that exactly in the world where I want it to be so we can measure it later. Then everything needs to go to the cloud. So we have all our images are streamed to the cloud.
Bas,
yeah.
Does this car make an image all around all the time, or does it?
Yeah. So every 5 meters we make an image. So we drive, and every 5 meters a new image is taken.
Okay.
So yeah. So here you see actually some of the dots.
Yeah.
This is one of our interfaces. You see every 5 meters we have dots, and yeah, we drive really every road, also like small roads, underpasses, overpasses. So you get like a very detailed map of the Netherlands or any other place you want to be. So we have a team who does like the web interfaces. So we have a couple of web interfaces. We have an API to our imagery, and we have a couple of connections to S3 software, but that's geometrical software. Probably not something you heard of. And then finally, we do something, or we want to do something clever with the data. So that's mainly my focus and my team's focus. And so that's the last group where we actually try to recognize objects, but also make 3D of the data. So basically my focus is in information products, so making inventories of objects in the world. And traffic sign is there, I think, the most typical example of. So we sometimes do client-specific solutions, and finally, so from our data we can make 3D models. We can texture the world. Actually, nowadays the 3D models we even have LiDAR on the car. I'm not sure. Anybody heard of LiDAR? Mm-hmm. It's this laser scanner. It's super cool. I find it super cool. But you find that, yeah. And we can locate traffic signs and light bulbs. So maybe a small demo which has nothing to do with machine learning, I understand. Oh. And of course that fails on me now. It's on the other screen. So you might recognize this city in 3D. So this is Amsterdam, and I think this is quite old. But the cool thing is you saw us zooming in, which is from aerial images, and then this is all from street view images, and we have like an entire point cloud which is meshed. And sometimes it's not so nice because yeah, you have these, you cannot look behind the car. Your car doesn't see anything there. But yeah, so we are at the museum. I think I'm going to the Rijksmuseum. So one of the things we noticed is that once we had this is an explosion of data for our customers. They couldn't deal with this large amount of data. But then again, it's a cool demo, and nowadays we have this even better with LiDAR-based point clouds. So this was all done from imagery. And yeah, so I think one of the strong points here is that we could combine the aerial imagery with street view imagery, which actually Google doesn't do. If you look at Google, they do some things better than us, but one of the things we did here better was sort of this direct combination.
Well, actually, Google is using aerial imagery to guess the size of the building. So you can zoom in.
Yeah. So they have the oblique thing. I totally agree. But if you zoom in too much, you jump to street view. Yeah. Now we are aware of a competition. We should be right. Yeah. So other information products which are really obvious for us are, we need to blur the faces, of course, and the license plates. So that's the first image you see. So here, actually we blur all faces, license plates, and that's all fully automatic. So we find light poles here, which was for one of our other customers. And here from aerial images, we were able to see what's the difference between the Dutch registration, which is called the Bach, which is a card of all the houses in the Netherlands, and the add-ons to the card. Yes?
You also use the AXN public data set for Livestream data.
No, and we know of the existence of the public data set. The problem with the AHN, which is a point cloud of the Netherlands, is that that data set is flown in multiple years. And so our customers, so especially for this solution, wanted to update every year. And so we calculate these, from these images, we also calculate point clouds, but then based on stereo vision. And our images are every year up to date. And so our customers could every year get a new update with this solution. And with the HSN, this is not possible. It's I think over 5 years, they will fly the entire Netherlands and make recordings of the entire Netherlands and then combine it into one big map. But yeah, nowadays I think we can do even better, but we didn't try it. But I'm not here to talk about all our cool products. I'm here to talk about one cool product, which is traffic sign. And yeah, so the challenge was really finding every traffic sign, and I will sort of highlight the challenges a little bit more. Then I will go into machine learning details. Then I will tell why we still have a manual part in the pipeline. I will give some results of the pipeline, and finally I will end with some conclusions. So the first challenge is that these are all the traffic signs in the Netherlands. It's our 500 classes of traffic signs. So if you have a self-driving car, you don't need like all these classes. These are parking space things and stuff like that. So usually for self-driving cars, they limit the amount of classes. Our challenge, because we were working for a maintenance company, they want to maintain the traffic signs. They wanted all these classes. It was really a lot. So the second challenge is our cycloramas. So the nice thing of them is that they work sort of as a round image. So from there you can sort of pinpoint. And if you can imagine if you have here 5 meters next to it another round image, I can pinpoint from another side and I get a world position. That's sort of stereo vision explained in 10 seconds, in my opinion. And so these are really nice images. So you shouldn't think that it's a challenge. However, they are currently 100 megapixel images. We still have also 10 megapixel images. That's a lot of megapixels to search for a very small traffic sign. So this is like the normal size of a traffic sign, and we have to be able to find them on 5 meters further away, because then we get that we have to have multiple detections. And the other challenge is that you see a couple of cycloramas and you see already the difference. We have these very dark ones, which are driven in tunnels. We have light ones. So we don't drive with really bad weather, to be honest, because we get all drops on the lens, and that's not so nice for our customers. But yeah, we have different kind of skies, different kind of lighting conditions, and we drive everywhere. So we have a lot of variety in image data. So the pipeline we then proposed was first detect a traffic sign, then position the traffic sign by finding the traffic sign in multiple images. Then sort of from these multiple images we can calculate one point in the world. And then finally say, okay, given that we found the traffic sign, it's this type of traffic sign, which is again a new challenge. So I'm going to first do the detection, then I'm going to discuss quickly the positioning, and then the recognition I will almost skip, because in my opinion it's not too interesting, but let's see. So the main categories. So in order to find these traffic signs, we defined a couple of categories. So we have the main categories, which I think are sort of the most common ones. Then we saw that the most common ones have like outer and inner things. So usually they are sort of in a white border or a yellow border or a black border. And then finally you have like a couple of very uncommon ones where we have separate detectors for. So actually instead of having one detector for every traffic sign, we have like, I think 20 detectors running for all these different categories. So, and then actually the overview of the detector is sort of given an image. We scale the image to different scales, which is called the scale pyramid. And then we slide the window over the image, and every location of the image, so really we slide it with I think 5 pixels. Every location we search for the traffic sign, and we do it over and over and over again. This looks really slow. I'm going to later show you how to speed this up. So these images are, yeah, we sort of calculate a sort of feature space, which is the Hoch feature space. It stands for histogram of gradients. Sort of looks like this. Then we use a support vector machine to find like possible windows in this image. So you get like a collection of windows because often you find the traffic signs on multiple scales. And then we try to combine all these windows with a mean shift approach, and then you get only a couple of windows where the real traffic signs are. So my question to you, how many people understood, are doing something with machine learning? How many people knew the term support vector machine? Okay, so I try to go slow. I think in some cases you can catch up, in some cases just leave it and you catch up later. So we explain the algorithm in a couple of steps, and later on you get the positioning algorithm, and that's another algorithm, and I think that's becomes simple again. So I first talked about this histogram of gradients, which, yeah, you have an image and you want to put an image into an algorithm. Nowadays, I would use a convolutional neural network, but in this case, this algorithm is a little bit older, and this was at that point the best we could do. So you can see an image as a bunch of pixels, and these pixels have difference with each other, and these differences we call gradients. And these gradients are in certain directions. So these arrows are where you go from white to black. And you can sort of, these arrows you can sort of put into a histogram. And then per sort of cell you have here, you can sort of visualize these histograms in the image again, so which line is dominant. So you get these kind of images. And so for this person you get this image. So then you have all kind of choices. So you can choose the number of bins, so the number of directions you want to have. You can choose the cell size of these blocks. So that's all nice. And you can say, is this the same gradient or is this a different gradient? So yeah, you have to set some choices. I'm not going to explain which choices we did because that's sort of the company secret, of course. But then from all these things you get like for a small patch you get a lot of numbers, and you get a set amount of numbers which we call a feature vector, which you can throw into some machine learning algorithm. So let's think that these machine learning algorithms are very simple and two-dimensional. Makes my life easy. So everything which is two-dimensional I can plot on a board. So then what you see is, so we want to separate the two-dimensional blue points from the red points. And actually what the support vector machine does, it makes sort of an ideal line where you have the sort of obvious distance between the red points and the blue points. And that's all magic, which you should let your computer do instead of doing it yourself. You have libraries for this. You sometimes see that the point is misclassified, but the clue here is that we call these points, which sort of make up this line, we call them support vectors, which is a really simple representation, and you only have to have a couple of support vectors to sort of calculate an optimal line. So the trick here is that we can do nice trick with the supports vectors machine, which I can show you later. So one of the things is that, so if you see here, so I have only 300 positive examples, but my entire image, if it doesn't contain a traffic sign, is a negative image. So from this image, I can already calculate 3 million negative samples. So I have a huge imbalance in data, right? I need to do something clever, so if I train the support vector machine, it is not able to deal with it. So the clever trick what we played is, so you have these two data sets. From that you, in the first step, create the support vectors. That's still relatively easy. You have sort of this optimal line which is formed by a couple of points. And then you run another image. So you get a lot of negative examples. And you know there's this line somewhere over here, and you know a distance to this line. And that distance to that line, that sort of is also, so the points which are close to that line, you actually want to keep. So actually the other points, they are too easy, you throw them away. And then on this thing, so on these points, together with your already found support vector machines, you train a support vector again. And doing this a couple of times, you get like a closer distribution between your positive and negative examples. That's basically the trick we do. We do that like 100 times. We have a pretty good classifier already. So support vector machines, yeah, if you're really familiar with them, you have linear and non-linear. We choose for linear. That is really because then we can also apply another trick. The other trick is you have this image, and if you have a linear support vector machine, given that you have here sort of the image but then in sort of values, you can make from your support vector machine this kernel. And this kernel, with this kernel we can do a convolution. And maybe some of you heard about convolutional neural networks. This is one of the most simple convolutional neural network you can think of. It's a one-layer convolutional neural network. But the nice thing of these convolutions is you can do them very fast, both in a CPU and in a, both in a CPU and in GPU. Currently we still do them in CPU for costs, but yeah, you can also do them in GPUs nowadays. And what we actually, given these kernels, if you are from an electrical engineering background or maybe even from a good computer science background, you might have heard every convolution you can do in the FFT domain. And in the FFT domain, expensive convolution becomes a multiplication. So we convert all these images to the FFT domain and do it there. That is cheaper. However, you can imagine I had a 100 megapixel image. Having that in memory alone is already expensive. And then if I want to run a kernel of this image, I need the kernel of this exact same size. So I have it twice in memory, which is really expensive. So there is another trick we apply, which is the overlap add trick, where you can sort of cut the image in parts. The parts are as big as sort of your filter. You put the parts to the FFT domain, you put it to the inverse FFT domain, you get an output. The next part has to have some overlap with the image. You continue like this, sum them up, you get the image back. And this saves a lot of memory. I nowadays think that like the TensorFlows and cafes and stuff would probably do the same for you. We at that time still had to do it ourselves. Nowadays I think this is solved. So now we have this output image. Actually, sort of this output has in the image has spikes, and where the spikes are, there are the detection windows. So then we have like a lot of detection windows on where objects are. And actually, we don't want to have a lot of detection windows. We just want to sort of have the average detector window. But you can imagine that if two people are walking quite close to each other, you might have overlapping detector windows. So you want to find sort of the clusters which are most obvious. And for that, we use a clustering algorithm. and the clustering algorithm is mean shift. It's a very simple idea. So you have sort of these two clusters. So these are again two-dimensional vectors. So we have a lot of these detection windows, which are a lot of these red points. And what we actually want to achieve is to find sort of the cluster means, right? And how we do it? We sort of make random a couple of these circles around our solution. And for these circles, we calculate the mean. And then the trick is, we go towards that mean then. So all these circles are sort of, we make a step towards the mean of that cluster. And we repeat this several times, and you end up sort of in your cluster means. Which is a really neat trick. So this algorithm has one parameter, and that's the size of the circle, so the radius of the circle. By that parameter, you can easily find cluster means in almost any complex clustering space. So really nice trick. We use this to go from these sort of really dense detections to a couple of detections. Okay, so now we found a lot of these traffic signs in our images, but then we still have to know where they are in the world. And you can imagine our images are cycloramas, so they go round. And sort of, if you find the traffic sign in them, you find sort of a ray in the world space. I already draw this again in 2D space. And then you see here that if I from multiple positions are going to draw these rays, again clusters appear of points. We use again the same trick, the mean shift, to sort of find these cluster averages. We can even sort of sometimes back project to the image, given that we know the position, and that is also how we find the 3D position. So this is drawn in 2D, but these lines we can also draw in 3D, and then we find actually where the traffic signs are in the images. So quite simple technique, quite elegant in my opinion. Finally, we have the recognition. So the recognition algorithm uses, we actually have two choices, but to be honest, this algorithm is not used anymore. So this was a key point descriptor with PCA, then a bag of features, and then a support vector machine. So the support vector machine is, I think, I just explained. These algorithms I'm not going to explain, but nowadays we use a deep learning network with a softmax at the end. And to be honest, most deep learning networks nowadays will solve this problem for you. Just recognizing from an image the traffic sign class. Then there are some things, some general comments. So running the detector is very expensive for us. Once you have these small images, running them, that's recognition is cheap, positioning is cheap. So running the detectors, there's the expensive step for us as a company. We found out that more specific detectors, so if you have more traffic signs, you get a better performance. However, if you have too much traffic signs or too much detectors, then it becomes too expensive to run it over all these images. So there's for us a trade-off in expense of having too much detectors or not enough detectors.
Because you have to run all detectors over every image.
Yeah.
Okay.
Yeah, although we do some tricks there which make it cheaper, essentially you still have, for every detector you have just X amount of calculations adding to your total sum of calculations. Finally, we found that the detectors often find classes which are very similar, and then our recognition has to solve this. And I think one of the nastiest problems we see is that, so given this sign, this is a separate sign, this is a separate sign, the entire thing is a separate sign. So there are in that sign already 20, 30 signs, and we see this a lot with other problems. You think you solve the problem, and then you get into these kind of problems where you need to have some kind of rule base to do the checking. Finally, so I think this begins the discussion, why do we still need humans? So these are our precision recall curves. So recall basically means that everything you so this is the trade-off between everything you find and not find. So given that you drive somewhere, you miss a traffic sign, then it will be on this axis. Given that you find something which is not a traffic sign, but some other rubbish object, then it's on this axis. And actually what we do is we try to optimize this axis a lot, and actually we are somewhere over here in scoring. So we try to achieve like the 98% because our customers want as complete data set as possible. And then we take these errors for granted because we can easily, with a yes/no tool, sort of remove these kind of errors from our data. So that's the trick we play.
Can you explain why do you optimize for recall and not for precision? Because I would expect that precision is important, that you detect the
Yeah,
right
so if we miss a traffic sign in the world, our customers have a requirement. We need to find 98% of all the traffic signs in the Netherlands. That's the requirement of the customer. So if we would miss one, that's a big problem almost. If you want to have these achievements.
So it's more important to find a traffic sign than to understand what the traffic sign is.
No, so actually this precision we solve by humans, or this precision where so sort of if we found too much traffic signs, I will come to that a little bit later. We let sort of people in Turkey, Mechanical Turk, review these traffic signs or these possible locations of traffic signs one by one, and they say yes, no, yes, no, yes, no, yes, no, and that. So the one option is to improve the quality. We had to go to all our images. That's too much. However, giving them the yes no tool, it goes really quickly and it's really inexpensive. So that's the trick we play. I will come to that a little bit later. So one of the problems we always have is exceptions. So you see here, these are actually not traffic signs, to be honest. Maybe even a little bit discriminating. So yeah, it's nice that somebody makes a house like this. However, I didn't think our customers were really interested in these kind of traffic signs, which they are actually traffic signs. And this is, I think, the case we see a lot, like somebody turned 50. It's really annoying. And then you have to maintain this guy. Yeah. So our manual process has sort of this option where, yeah, if there is a nonsense traffic sign, so we apparently found the Albert Heijn sign, which is one of the big supermarket brands, which has a blue sign, looked according to our detectors a lot like a traffic sign. So we find it a lot, and then sort of these people in Turkey again, they get them out for us. Ideal. And then finally, we have another step where people just check like the situation where they are in, because yeah, you can imagine that yeah, if you look in the small context to this traffic sign, you would say yes. However, if you look at the bigger picture, you say okay, this is traffic. So we have a visual interface for people checking these traffic signs. And then of course we have quality control steps of both places. So basically this yes/no tool is really simple. It goes really quickly for people who are doing this work. If we get unacceptable results, we send it back and they have to have a 2-person agreement. If we reject it again, they have to have a 3-person agreement and so on. So we can always guarantee the quality. That's fine. The other thing is, yeah, so we needed to show to our customer that we were good enough, because they wanted to know how good we were anyway. So one of the things we did was, given the Netherlands, we took a couple of these blue circles in the Netherlands and we checked, given random blue circles, how much traffic signs were present and how much we did wrong and right. And then we have a performance goal of 98, and we can, with some random sampling, which is a technique to given a random set, show how good you are. We can, with a confidence margin of 95% and with the margin of 2%, we can indeed show that we usually reach this goal. If we don't reach this goal, we can still go to the manual step. But actually, our automatic system, almost everywhere you reach this goal. So that's a nice thing. So actually, we already finished this project for 1 year. So we have all the traffic signs in the Netherlands. And then the customer came back and said, let's update all the traffic signs, because a lot of traffic signs are sort of stolen and stuff like that. So now we have the new challenge of updating this database every year. So we have a couple of tags. So you have added, removed, and matched. So if it's matched, you found it last year, found it this year. It's not too much work anymore. Only the added and removed you have to check again. So yes, this is a reduction of work. We sometimes see mistakes of the last year database. We sometimes have problems with the positioning of the car. You can imagine that the car knows very precisely where it is in 10 centimeter radius. However, in the big cities, because of GPS problems, because of large buildings, we don't always reach the 10 centimeters, and then we might have two traffic signs next to each other. So we have all kind of tricks how to deal with these kind of things. And currently our statistics show that we improve our traffic sign set every year, because you will drive next year with again a 98% accuracy, and you already had a set of 98% accuracy, and then it becomes a set of 99% accuracy. Well, that's what we are now seeing. So some statistics. So this is the number of recordings we processed. So this is actually the number of municipalities processed, and yeah, currently we are over the number of municipalities in the Netherlands, and we process even more. So these are the number of traffic signs in the Netherlands. So we estimated that around 20 traffic signs per kilometer in the Netherlands, which is quite large. And
this is images or frames, or what is it? What is a recording?
Recording is a panoramic image which we take every 5 meters. You missed the beginning.
Sorry.
This is apparently the longest traffic sign in the Netherlands. So, in conclusion, we presented the system that found every traffic sign in the Netherlands. I have to say it like this because, okay, we have a 98% recognition or recall. So we have the first set of all traffic signs in the Netherlands, and we are now updating. The current system is a combination of both automatic and manual steps, which is a good combination between very high quality and an acceptable price. We ensure the quality of our data using random sampling procedures. And we are checked by DNO now, and they agree with our performance. So that was great. Yeah, we always like to be challenged for other objects, but it needs to be large scale for us to make profit out of it. Yes?
Okay. Could you maybe give some examples on how you would use that database, like what cases do they use?
So currently I think there are a couple of things they are thinking of. One is, so our customer we sold it to is really into the maintenance of traffic sign. They sell us some kind of solution where they put like LOT devices on traffic signs, and yeah, given that traffic signs are missing, they will replace them automatically, and they will use our data to see if traffic signs are missing and what needs to be updated. Another thing they were talking with TNO about is, of course, self-driving cars. Because, yeah, you have a map of all the traffic signs in the world, why not start using it? Or, not in the world, in the Netherlands, okay, sorry. Our further vision of the world, of course. Yeah, and so, yeah, all the things in between, maintenance, but yeah, the current goal is really maintenance.
So how fast is the detection algorithm? Can you use it for self-driving cars?
No.
So how long does it take?
So first of all, we have like high resolution images. So currently, I think it takes 3 minutes on one high resolution image. However, that's done a little bit on purpose because we are using cloud computers, and we found out that the cheaper instances are better to run, and then you are a little bit slower, but in price that will be cheaper for you. So to be honest, it can run faster, but it is not designed for sort of the self-driving car because of the high resolution images. So I can run the same algorithm probably on what a car records, but actually a normal recording device on a car is much lower resolution. The same algorithm will work and also work faster. But because we have like the 100 megapixel images, the algorithm is made for that, or we optimized it for that. Yes?
I was just wondering, because you're using basically a sliding window for detecting the traffic signs, right?
Yeah.
Have you looked at YOLO types of algorithms?
Yeah, actually, yeah, we're looking at them. We found out that the trade-off, or currently we are sort of in the, yeah, should we go to convolutional neural networks? For other solutions we already do. For this one, it seems to be still a little bit cheaper.
Right. Okay, because especially self-driving cars, etc., they do object detection real time, right? And I've got it running on my laptop real time as well, and it's not 100 megapixel images, of course, but
no. So I think the problem we saw is in the cloud. If you use a GPU machine, it's 10 times as expensive as like a normal machine.
Right.
And because we at that time didn't even have GPU machines in the cloud, we optimized it for CPU machines.
Right.
And now it's still a little bit cheaper. And at a certain point, I will see in the cloud that there will be a trade-off in
prices. Okay. Well, yeah, it goes too much detail here, but I think if you're looking at YOLO, you know,
yeah, I know the algorithms.
Because one thing is, what you said is you have all these sliding windows that have no hits, right?
Yeah, no, but actually, this is also a convolution. It's almost the same.
Okay.
But it can really help. If you just make the math, so 6 minutes, 3 minutes means simply if you have an order of magnitude faster, which you can do if you make a local calculation.
Yeah, I think you should go YOLO.
Images, because normal self-driving cars have HMI instead of the 100 megabit images.
I can't go into details. So YOLO is running 20 convolutions in the first stage on these images. In the second stage, it's running 100 convolutions. We run 1 convolution. So if we already implement this algorithm on a GPU card, it's again as fast as the YOLO.
Yeah, but you only do one pass. Okay, well.
YOLO does also a pass.
Okay.
Just got 1 minute.
It's okay.
Yeah.
Yeah, I was just wondering, isn't the government keeping some kind of database of where they set the signs, or is it really a set and forget kind of procedure?
Yeah, so some governments are keeping some databases. So actually, around the highways, Rijkswaterstaat is doing a proper job. A lot of municipalities sometimes lose their database, find them again, didn't update it, did update it, stuff like that.
It's not obliged for municipalities to have this data.
Okay. Interesting.
I was also quite surprised. Yeah?
Yeah, I just wondering, so sometimes when you register for something on a website, they get people to pick out the traffic signs. So why didn't you take that approach? Or?
Because we don't have a website where people are volunteering to do that.
I think like in American companies, they kind of outsource it when people are doing captchas. So
yeah, so we of course outsource it to another company, the manual annotations, but yeah, our choice was another company which does it also in a cheap way, but yeah.
As I know, our eye always analyzes moving pictures. So that is, for that purpose, it always shakes our eye, so we don't notice it. But we always get moving picture for our brain. Have you? I think you have all the data. Have you tried to implement such kind of algorithms when you analyze not one image but several neighboring images?
Yeah, so we don't have all the data. We don't have a movie because our images are taken 5
But you
meters.
have something like 2 images within 5 meters. Maybe
Yeah, so
you
you
play around with this.
yeah, so we actually played around with the concept, and it looks like it is working. That you can sort of, but it's for us recently working with a lidar, where we can sort of see differences in imaging and stuff like that. But this doesn't really work if you have these big intervals, or it didn't work for us. Let me put it like this. Last question.
Since you're at DigitalOcean, can you tell us a bit more about your cloud infrastructure and whether it's how does it work? Like, how do you do the schedule your jobs? Is it like
I can quickly say probably Azure Condor, and yeah, that's sort of it. I think Azure Condor. Yeah, basically we do a lot of stuff with Condor in Azure, and we have a lot of computers doing that for us.
sorry? Come again?
Do you know Azure, which is the Microsoft Cloud solution?
Yes.
And we have a Condor, which is a very old system for running multiple jobs on multiple machines with a queue-based system.
How do you do scheduling? So do you do some like batch jobs, or do you have like the customers asking for some data set and then you select the data set?
Yeah, so basically what we do, we divided the municipalities and we send the municipality, and that will be cut into first in a lot of images, and then we process the detections per image. Then for the positioning, we sort of know where sort of neighboring areas are. So a couple of jobs are then after detection spinned off for processing areas, and then these areas are also thrown into the recognition algorithm. So it's sort of a multiple stage approach which works with a quite simple Postgres database, and that worked all quite well for us. It was not that interesting cloud-wise, in my opinion, but sorry. Yeah, or so we don't store the images. We store references to the images. The images are stored in blob storage. However, sort of all the things is just a relational database where we use this, and that worked for us.
No Mesosphere, no Kubernetes, no Lambda.
No, sorry.
Just get out of here.
No, yeah, we I think it partly had to do with that we so we first had a couple of PhD students working on it who made like a sort of first system, which is already quite old, and then so we took a couple of these very stable technologies and keep using them, and then not switching too much. And at a certain point, our company decided to go to the Azure cloud, so we did that.
How many boxes are you running?
I'm gonna have to jump in because otherwise it's going on forever. Yeah. Are you gonna be here for pizzas?
Yes.
Great. If you have any other questions, by the sound of things, loads of you do. Yeah, we will be doing pizzas afterwards, and so you can chat through pizzas and beers. Yes. Thank you so much for a really interesting
no problem.
Yeah. Then we're going to take like a 5-minute break whilst we get the speaker set up. Hopefully there's some beer left. I can get some more. News. Yeah, so yeah, we'll start again. I put some more beers out, so that's great news. Everyone got a chance to have a chat, so that's great. Right, before we start the second half, we have to do the raffle, because that's very important. Now, I lost the raffle tickets, so we have to go like really new and exciting. So I have a very technical spinner here, as you can see, and I put all your names in this spinner. And obviously it looks gross because it's not designed to have 107 names in there.
Did you do it manually?
No, it's a copy and paste job, thankfully. Hugo tells me I need to tell you what you can win. What you can win, we have DigitalOcean t-shirts. We have unisex and girls. And we also have in here, courtesy of O'Reilly. Let's get the right one. We have a book that tells you how to do machine learning. So that's really helpful and kind of on topic. So we have to thank them for that one. But so this will be the last prize. The first two just get a t-shirt, which is still pretty cool. But yes, here is my very technical way of choosing people, and hopefully it's vaguely random, and you should be in there. The rules are: I will call the name out that comes up on here. If you don't answer within 5 seconds, we redo it until we find somebody who does. So remember your name. It also has like sound effects. Okay, this is a really hard name to do. Gaia Luca? Yes? Yes! No! You're a winner. Like, you have to have it. No, you refuse to have it. You're like, I want to be the last person. Okay, remove your name. Next person. Okay, Ahmed? Yes? You're a teacher. Yes? Yeah, come on up. Yeah. You have to fight your way through somehow. Whilst you're here, what size t-shirt are you? We can get it whilst he's walking, but it's fine. Okay, what size t-shirt?
Extra large.
Extra large. Can I ask you to do the t-shirts? I will get the next person. Yes, come on over and talk to Hugo. He will find you a t-shirt. He's great at choosing t-shirts. Okay, so you get removed from the spinner of doom. Oh, and it refreshes. Oh, lovely. Okay, right. Next person for another t-shirt. Lena. That's an easy name. There we go. Yeah. You have to come on up and grab a t-shirt from Hugo. And then for the grand prize, we have to remove you from the list. There it goes. The grand prize, the book and the t-shirt. Eek? 2 E's and a K? Eek? This is not an English name. No, nobody named. Okay, right, you got removed. Still, the tension is like palpable. How about Elizabeth? There we go. Yeah. Okay, cool. Right. So yeah.
Yes. What size t-shirt do you want? What color as well?
Okay. Yes. So I'll give you the book. Congratulations.
Thank you so much.
And then you have to cue to Hugo. And then in the meantime, I can then introduce the next speaker. And it's a bit claustrophobic, but we're good. Okay, so that's the raffle done. And I actually have an introduction for the next speaker. I had them for both, but I didn't have a piece of paper. Yeah, Daniel is the CTO for Picnic, the world's fastest growing online supermarket that makes grocery shopping simple, fun, affordable for everyone. Previously, he's the director of R&D for Fredhopper, responsible for the product and technology roadmap, and led an engineering team located in Amsterdam and Sofia. Daniel holds a PhD. Bas also holds a PhD. They're both doctors, in computer science, and he has an MBA, just casually. He published papers, edited journals, and chairs international workshops, just when he's like chilling, just why not? And his workshops are on software correctness. He's going to give us an inside look into machine learning at Picnic, and hopefully that'll be really interesting. Yeah. Can we give him a warm round of applause?
Yeah.
Great. Okay, good. Before I get started, it's really great to be at a more technical crowd. So I'm giving from time to time a couple of talks, more kind of a business environment, but it's much nicer to do it in front of a few people that are doing a little bit more technical stuff. I hope that the connection works. Before we go into that, who has actually heard about Picnic? Just show of hands. Well, that is nice. Keep up your hand. Who has actually downloaded the app? Okay. Who has actually registered? Who has tried it? Who has played it in order? Who has ever? Great stuff. Great stuff. Okay, great. Oh, sorry. Yes. Great. So what I will do is I will introduce a little bit Picnic when we are back on the presentation. And then I will talk you a bit through what we are doing on the machine learning side. So our story started a couple of years back with a pretty simple insight that everybody is doing shopping online for non-food items. So you buy books, electronics, fashion online, but nobody is doing this for food. And what most people are saying, well, you know, if everybody is just buying non-food items, then we also need to build a non-food shop. But we thought there's an opportunity to build a shop that actually can deliver food. And that is more or less how we got started. And the interesting thing about the display. And we thought a little bit about what could be the reason that nobody is shopping for food online. And we identified mainly 3 reasons. People don't want to wait. So a delivery that actually has a delivery window between 4 and 8 is not good enough because you don't know if you can use it for dinner or not. And nobody actually wants to shop in a cumbersome way. So you want to have easy shopping. You don't want to go through an interface that is optimized for 2 or 3 products, but more for kind of 30 products. And the third one, and it's a very Dutch one, nobody wants to pay too much. So that means you want to actually don't want to have delivery fees. And that was the starting point where we thought, well, the proposition is a pretty simple one. We want to deliver on a mobile, so it's the convenience part, all the groceries, so everything what you love, to the lowest price, on time, to the doorstep of your house. And if you like, even to the kitchen. So that's more or less the kind of the starting point. Let me show you a bit how it looks like from a consumer angle, and then we make a deep dive and a look behind the scenes what you see, how we have built this up. This is a small one that should work. Lots of happy cars. So in practical terms, that means technology-wise, there's an e-commerce system, so to do the online shopping, and there's an entire backend to make the farm-to-fork connection. So there's a warehouse and all the kind of systems to manage the warehousing part, and there are all kind of systems to organize the logistic planning and the logistic execution. So more or less, just this last slide about, let's say, the introduction of Picnic. We are now active in around 35 cities, have a pretty large set of suppliers of local and global products. So this is a kind of the big difference to the classical retail, that we also organize, let's say, that we have retail of a lot of local products that are just local to a specific city. And we are delivering in those 35 cities with our own fleet, so around 400 vehicles we have now. A pretty large set of global products with the lowest price guarantee. It means simply that you need to know all products of the entire market, that you can just check what is the kind of the lowest price, and then you match it with the prices here. And we have now a little bit more than 100,000 customers. Since the last weekend, we are also active actually in Germany, but so far our base was mainly in Netherlands. When we started with Picnic, there was one major insight that we had, and that is something which goes already a little bit back. This is a quote from Roy Amara. So Roy Amara is a kind of an engineer from the 60s who has made, let's say, the observation that if you want to be really successful in technology, and if you invest in technology, then in the most cases, on the short term, you're a little bit over-optimistic. You just expect a lot out of it. But on the long term, you're always underestimating it. The impact of technology is something that most people on the long term underestimate. And that is more or less everything what we're seeing now in AI and machine learning is something what took a long time, what a lot of people have for a long time overestimated. And that's the reason why there has been so many AI winters. But on the long term, this will be, the impact will be massive. And I will show you a little bit on what we have been doing in Picnic that is going in this direction. And the way as I want to show you this is that I show this by challenges. And the challenges means the kind of the tasks that we wanted to solve for customers, and where we used actually machine learning for those. The first one is that we have a so-called what we call the mobile shopping challenge. And mobile shopping means we want to make it possible for customers to shop in a pretty short time a large number of products. So if you use one of the typical Dutch stores like Coolblue or Wekamp or any of the other ones, then you shop typically just for 2 or 3 items and takes you easily 10, 15, 20 minutes because you browse through the entire shop. And it is normal because if you buy now an iPhone, you will not buy the next time again an iPhone. So you buy always different items. But the food shopping challenge is a completely different one. What you do here is you buy week over week to a large extent the same products. Doesn't matter how hipster you are. In essence, you're 60 to 80%, you're buying simply the same products. So that is something which is pretty convenient for a recommender system, because this is a kind of a challenge that most recommender systems have, that you never buy again the same product. So you need to learn from other customers. But we can learn just from the customer itself, because whatever he bought last week is pretty close to what he will buy this week. Not exactly the same, but it's close. So our journey started with actually observing that if customers shop for a shorter time, then the likelihood that they check out, that they come back again to the shop is higher. So therefore, let's just make the shopping journey a little bit shorter. So we started now with a journey which was around 400 milliseconds in 2016, and we brought it down then a year later, well, a little bit less as a year later, to something like half of the time. That is the kind of the journey I want to talk to you a bit through and how we have done this. First step was, well, let's make a hackathon and let's see what we can do actually with deep learning and machine learning. So we built a deep learning network. But before we go there, let me tell you a bit what is the kind of the challenge that we try to solve. The challenge that we try to solve is that we want to actually allow customers to shop in bulk. So every kind of recommender system, if you go to Amazon, allows you to add additional products. So you get one product one by one recommended. Recently, Amazon also started to offer kind of 2 or 3 products in one go. But the real challenge is if you want to offer 4, 6, 8, 12 products in one go, then this is only efficient for you as a customer if actually all 12 products in one go are actually the right products to recommend, because otherwise you wouldn't make a one-by-one pick. So the challenge here is that you want to recommend a lot of products, typically up to 12 products. You want to offer the functionality that you can shop with a single tap. And then you want to actually have a recommendation confidence, which is at least 80–90%. It's pretty simple. You want to recommend only those products that customers really like. So most recommender systems are just useful if you recommend, if you have a likelihood of click-through which is at least 50%. We went a little bit further, which is more kind of a confidence of 90%. But the challenge that you get in this context is that if you have actually a recommender system which can offer you a precision of 90% for a single item, then for 12 items in a row, you have 28%. That's pretty simple. It's 0.9 to the power of 12. So therefore, actually 28%, that means for 70% of your customers, 2 out of 3 customers, you will recommend products that they don't like. So this is not good enough. This is just a crappy feature. So therefore, you need to go a step further. So if you want to have 90% of precision for the 12 items, then a single item precision needs to be at 99%. So that is an extreme high requirement for recommender system. And then you have for food a couple of very specific challenges that usually other shops don't have. You have a seasonality effect. So at some point you have some fresh food which is just available in June or July. Then you have actually variations. So that means at some point you have tomatoes that come from Spain and some tomatoes come from France. And then you have event-based buying. And event-based buying is a pretty simple thing. If you have events like, for instance, Outmarkt, if the cultural season starts, then everybody eats usually either out, or if they eat in, then they eat a very different type of food. Similar way also for Christmas and for Easter. So this is a very special environment. So the next step, by the way, if you have any question, just interrupt me so that everything stays clear. So the challenge on a formal level, I don't want to show you, I will not show you too many formulas, but one simple formula I show you, and that is a formula which actually such a recommender system can be formalized. So likelihood that you buy the next time a bottle of milk based on your shopping history. And the shopping history is a pretty simple one. You just look into what did you buy 4 days ago, 7 and 9 days ago, and that is in this case like a Nutella, and here you have some Tony Chocoloni, etc. So that's more or less the kind of the basic setup of a recommender system, and that exists already at least 15 years. And Amazon has done probably the biggest breakthroughs there around 2000. So starting from this challenge, we made a hackathon. Yes.
Your recommendations come from only your own story?
Yes. So what we do is we are using only the own customer data, let's say our own data for the recommendation. So some recommender systems actually use market data for the recommendation, but this is something what we don't do. Yeah, no.
Isn't it a problem because of the first impression? So
So the question was, is this not a problem of the first impression? And this is called in recommender system the so-called cold start problem. That means in the cold start problem. And that is something, in essence, you don't have a history. You just try to recommend, you try to understand what can you recommend if there is no history. So what usually you do in this case, you build the average of all existing customers. So you assume this is a customer. What is the most likely thing if you have no knowledge about a customer? So that's more or less how kind of the cold start problem is solved. Usually you have a little bit more than just the kind of than no history, but that's more or less how this is resolved. So first step is building a neural network. That's exactly why we are here now. So what we now build is you build a neural network, and it looks a little bit complicated, but in essence, it's pretty simple to explain. You have some input, and the input is just the history, where you say, okay, the last time he bought 2 weeks ago one banana, and 2 weeks, then he bought 3, and then he bought 2. And the same way then also for wine and then for Nutella. That's a simple kind of the input. And one of the interesting and important learnings, and if you try this yourself, is you should not use the dates, so when he bought something actually, but that you take a kind of a cohort analysis, that you say he bought it 2 weeks ago, independent on what is the current date. So that means you are simply saying when was the last shopping and when did he buy this before he just take the deltas between 2 shopping trips. Then you have something what is called hidden layers. I won't go too much into technical details, but this means simply on how do you model different aspects of your data. And what we saw there is that one thing is the item-item relation. So that means which kind of products are bought together. So that's something also very intuitive because you want to recommend stuff that you can use together for meals. Then you have item-day relation. This is something what maybe not everybody sees immediately, but people buy completely different stuff on a Monday than on a Wednesday, than on a Friday. On a Friday you buy simply for the weekend, and on Monday you buy for the week. Very, very different products. And then you have the items that day relation, which is kind of the combination of both of those factors. And then the output is pretty simple. You simply say, well, most likely tomorrow you will buy bananas, wine, and Nutella. That is in essence what such a recommender system is doing. The only thing what is really interesting now to as a kind of a learning effect is we used the kind of a TensorFlow. We used a couple of different networks, but TensorFlow was the most efficient one, and we normalized the quantities. So what this means in essence, you want to actually get out the factors that if somebody is, if there's a person that is buying always, let's say, higher quantities, that he is overruling the kind of the learning of compared to somebody who is buying smaller quantities. So that is looks like a very nice nice network. You would expect great results, but the result was shocking. It is not good enough. The result is that the likelihood and the precision of the system is just 50%.
But for all 12 or for each?
So this is now for 12, exactly. So the interesting part, and one of the learnings is, everybody has probably heard about that you need a lot of data for machine learning. And that is also a reality that we saw here. So this is an experiment which we did around 9 months back. And at this point in time, we simply didn't have enough customers. We didn't have enough data to actually train the network. So we tried to understand what is the reason for this. And there are mainly two reasons. One reason is called shallow data. Shallow data means the history per user is not deep enough. You just don't have enough shopping cycles for a single customer. But there's more. And this is something what is actually called that the data is not breadth enough. You don't have enough customers that actually have done a single shopping trip with you. So the breadth of the data is not big enough. So that has been a big challenge. If you look a little bit in the literature, what people then tell you is you need to pre-train your network. So what this means in essence is you know roughly what people will buy, you train the network, and you actually get a little bit of kind of the cold start problem out, and you try to see how you get this out. But doesn't work well enough. And then we tried something which is super simple, but pretty effective, and has nothing to do with neural networks. Let me show you what we did here. We actually went back, and in the supermarket world, people have used since the 50s a method which is called RFM. This is recommendation based on recency, frequency, monetary. So you look only to your customers by when did you buy, which kind of products, how often did you buy it, and what is the value of those products. And the algorithm is something which actually you can easily explain on a simple slide. So what you take is, you take the last 10 orders that a customer has done. This is then on the left-hand side. What you do is, you just take the items that he bought most often. This is the 80% of the 10 orders you take as a kind of the candidates for recommendation. Then as a next step, you simply rank. So which items did you buy 8 times, which times 9 times, and which maybe 10 times. And the last step is, well, let's just filter out the stuff that you can no longer buy, because maybe Asperges is no longer available, or some other products are simply out of season. And then what you say is, well, just display between 4 and 12 products, depending on how many are leftovers. It's so simple that you would expect this not to be very effective. But actually, this is outperforming every deep learning network that we have tried. Every deep learning network. And it doesn't matter if you use a kind of, you saw there was an LSTM network, so this is long short-term memory type of network, which are most useful for this kind of setup, because you actually take the history effect account. So it's more important what you bought last week versus, let's say, last month versus last year. And you take actually also the frequencies into account. But this algorithm is just much better. So what we saw here, and we combined it then together, in essence, you need for effective deep learning, or for effective machine learning, you need kind of 2 factors. On the one hand, you need big data and deep data. If you don't have enough, if you have just big data, that means you have a lot of customer data, but for each customer just a short history, this is the left-hand side, then it will simply not work well enough. Because in essence, you did not learn enough from the customers. There's not enough depth. But if you look to the right side, if you have just deep data, then you have a pretty narrow data set, because just a few customers have this depth of data. So for instance, that you take something like 100 or 120 orders. Not many people have so often shopped with you. Then the recommendation is also not good enough. But somewhere the sweet spot is somewhere in between. The third step, and that is a kind of a combination of the first steps, 2 steps that we took, is that we said, well, we need to bring a little bit some machine learning and some aspects of this back. And then we thought, well, why not using some evolutionary learning and evolutionary algorithm? And that is something which actually is pretty simple to explain. So there's some initialization, and then you have a kind of an iteration where you say, you try to evaluate how good your algorithm currently learns. So you try to understand what is the precision of the recommendation. Then you build a new, kind of a new selection of parameters. You make a variation. So that means you try all parameters and then you evaluate again. And at some point you terminate. So this is a kind of an iterative mechanism where you try to learn the parameters of the algorithm I showed before in a way that you have a kind of a population and iterate different parameters. And that is pretty efficient to quickly come to optimal parameters. So if you look now, and now you see on the y-axis, let's say the precision of the recommendation. After just a couple of iterations, we start with precision of 45. We could grow up to the point of now a precision which is in the range of 85% accuracy of the right parameters of the algorithm we saw before. So that is a pretty simple algorithm, which is kind of evolutionary algorithm. It's still machine learning, but not really deep learning. That is good enough to recommend enough products. Here, what you see as a kind of parameters, you need to take 15 orders from the past into account, and you recommend 8 products. And then you have a kind of likelihood of 85% of the correct products that you recommend. So that was already a pretty nice result. So let me show you something what we learned from this. It's probably something what you can expect and something what is a bit surprising. So the first thing is, well, if people buy actually raw curry, then they buy also some kokos milk together. Well, it's probably expected because that is something what matches very well in your meal. But you have also something which is a little bit more surprising. If somebody buys some bio cleaner, then he buys this, the likelihood that he buys bio bananas together instead of no bananas is 10 times higher. So it's just a kind of a relation where you see if people have let's say a tendency to buy more bio-like products, then that is a kind of cross category. And the third category, well, if you actually buy Pampers, then it's 11 times more likely that you buy some biomilk. Well, you can come up with yourself with an explanation, but at least this is a kind of something what you see in the data. Good. That was the first challenge, the shopping challenge. Second one is something what we call the distribution challenge. So we have a distribution model where we actually drive with our own cars to customers.
Did you use for the first one basket analysis or something like that?
In essence, this is a basket analysis. So what you saw in the second slide, where we took the kind of the 10 last orders into account, is in essence the kind of the previous baskets that you shopped out.
Also from other customers.
Now we're using just the single customer history.
Okay.
So what you can also do, let's say as a kind of an extension of this algorithm, is that you don't take just the shopping history of the customer into account, but what he has currently in the basket. And here's something pretty interesting what you can do as a next step. If you can recommend how likely is it that a customer buys a product, don't recommend a product the customer will definitely buy. Because in essence he buys it. What you want to recommend is what he maybe will buy, so he likes it, but he will not anyone buy because he finds it.
Yeah, that's why
exactly.
For
yes.
other customers.
But there's a kind of a trade-off, so you need to be a little bit careful because obviously a customer satisfaction is something that you don't want to hamper with this kind of approach. Good. Distribution, meaning we are driving with our own cars to customers. It's a lot of fun with our own electrical vehicles. However, we want to make it convenient for customers, and that means a small window for customers. This means in our case that we have a window of 20 minutes. You see in the morning the kind of delivery window of 20 minutes, and then we want actually in de facto all cases deliver in this kind of very narrow window. So if you have now a route to a customer where you have just 10 trips, so 20 minutes means you have an ETA plus minus 10 minutes. So if you have now a route where you have just 10 stops, then after 10 stops, if in each stop you would just be off by 1 minute, you're already outside the window. So that's something super challenging. Yes.
How long in advance customers need to place order?
Yeah. So we have our business model is a next day delivery model. So which means you're actually placing your orders until 10 o'clock in the night, and then we deliver it the next day. So this means what happens technically is until 10 o'clock, you're placing an order, and then we make the entire route planning for the next day. And then in the morning we know what is the expected time that will be at your doorstep. Then we can communicate to you the 20-minute window. So as a customer, you select the 1 hour window. So this is the window that you select in the evening, and then the next day we communicate to you a 20-minute window, and that's the kind of the final customer contract that we have.
And how early in the morning, the first deliveries?
We do currently deliveries from 3 o'clock in the afternoon until 10 o'clock in the evening. So you need to be at home, so that's just more convenient in the afternoon. Yes?
Do you have any ability to call an emergency resources? So say at 10 o'clock this evening, you find tomorrow you have a full schedule, because I assume you allow people to order.
Yeah.
Do you actually call nature people or other companies?
Yes, that's a pretty interesting point. So what happens, in essence every kind of recommend system or every e-commerce site is doing, they have capacity limits that you can just, a specific amount of people can place orders for a specific slot. So that means if you select the slot for tomorrow at 4 o'clock, then they will just allow a specific amount of orders, because they know this is the capacity of the fleet that they have. And if you are simply, they allow 100 customers, and if you're customer 101, then you simply can't place an order for this shift.
But
so that's
on numbers, not necessarily the routing and the abort. Even if you have only your capacity, it may not be physically possible to reach all
Yeah.
the customers.
So that's the reason. That's the reason why you need to come up with a distribution model where you can pretty precise predict how long the intra-drop distance takes. So what you need to know, and that's the kind of the logistic magic that you need to do in such a model, is you need to actually predict how many orders can you fulfill in this single hour. So what you do then typically is you take a city, you split it up in different sectors, and then for each sector you know roughly what is the expected density of a distribution. So that means you know that in average you're driving something like 100 meters, 200 meters, or 500 meters. So therefore you have a total route, well, of let's say 500 meters times 10, 5,000 meters, and then you simply know how long it will take you to deliver to those customers. Then you will know the orders, and then you know what is the capacity limit. Yeah.
Do you always have your whole fleet available, or do you also use machine learning to know how many cars are you going to need?
That is a pretty interesting question. I won't talk much about this, but we're using also, so the typical thing what you use there is predictive maintenance. So what you want to know is, we have now around 400 cars. With 400 cars, then every day there are at least 5 cars are broken. It's just statistics. So you need to know which 5 cars are most likely broken. This is already the first change. And then what you want to know is it this time 5, or is it 7, or is it 10? If you buy all cars at the same moment, you know roughly that you won't have too much problems for the first 2 years, and you will have a hell of a lot of time afterwards, because everything needs to go to maintenance. So that is the kind of the magic that you do in such a logistics environment. You try to really understand what is the most likely, well, how many cars may break at the next day. It's the same what, for instance, in a typical hosting center like Google is happening. A normal hosting center like in Google or Amazon is around 50,000 servers. In such an environment, you have every day between 50 and 70 servers are breaking. Usually it's the hard disk. So the only thing what those guys are doing are mainly 2 things. They need to know how many sysadmins they need to replace disks, number 1, and they need to have a very efficient way to store in a reliable, consistent way on multiple storage devices the data that nothing gets lost. And that's more or less the kind of, for instance, the Hadoop file system that they have developed for this. Good. So the interesting thing in our case is we have de facto no-show. And the reason for this is pretty simple. If you deliver to you and you're not at home, you simply have no food. So therefore, actually, no-show is not a big issue compared to classical postal services for us. So how do we do this? What we have built is a kind of a regression model, and I want to talk to you a bit through how we actually predict on the actual drop times for customers. And the interesting thing is why drop time means how long we take for a single customer. Every postal service is optimizing the cars and the routes on the shortest time between different kind of customers. If, in our case, we have such a high density in the city, it doesn't matter how long it takes from customer 1 to customer 2. It's anyway just 50 meters, 100 meters, 150 meters. That is something what you can do super fast. What the difficult part is, if you stop at a customer, you need to actually find a parking spot, you need to unload the vehicle, you need to find the door of the customer, You need to ring the bell. The customer needs to actually come to the door. You need to give him the goods. He needs to give you back Staatsgeld and all kind of stuff. So that is something what takes actually much longer than going to the next customer. So that's the reason why we try to understand how long a single stop takes. So in this case, we actually predict the stop time of a customer by first taking account an area constant. So this is how likely is it to find a parking spot in this area? How easy is it to actually navigate this logistic area? Second one is it the first time customer? First time customer is very important for us because at the first time, you're spending a little bit of time with the customer. We're explaining the app. We are answering some questions. There's just, let's say, a little bit of kind of a protocol that we are following that makes it, that takes a little bit longer for the first time customer. And we want to take the time. So therefore, we are planning just another additional minute for the first time customers. Next one is then actually the actual physical goods that we deliver. So this means now here ambient and chilled. So we are working with different temperature zones that you get your frozen pizza also in the frozen way if you're at home. And ambient chilled means just a kind of regular products. And then frozen products we deliver. And then this is just a kind of constant on how much, let's say, how much products we deliver to the customer. But the real magic happens at the last point. And the last point, I just called T delta. But this means here we are taking into account parameters that are actually specific to the situation when we deliver to the customer. So one thing is, for instance, if we have a nighttime delivery, it takes us on average 43 seconds longer than a daytime delivery. And that is, and the explanation for this is, in the night it's a little bit harder to find a parking spot, it's a little bit harder to find the door, it just takes a little bit longer compared to the day. The other one is actually, where is the location of the door? Can you go from the front door, or do you need to go around the house and go to the back door? It takes an average around 57 seconds longer. If you go to the second floor instead of the first floor, it takes you 23 seconds longer. Because you need to walk a little bit longer. The interesting part is if you go to the third floor instead of second floor, there's no difference. So that is just going a little bit up is more or less the same. And then of course you have some constants. Is this a kind of a driver that has been already for a long time with us? So he knows his neighborhood, he knows his customers, then obviously he finds it a little bit easier the customer, or is he just a bit fresh with us? The same way also the kind of the vehicle. So this is kind of a pretty simple model that we have implemented to actually understand how long will it take. Let me show you a bit how this looks like from a customer angle. So as a customer, what you do, it's Dutch, but I hope that everybody understands at least the basics here. So what you do is you just select when do you want to have your groceries delivered. And now you select, okay, we will deliver tomorrow between 6:15 and 7:15 the groceries. The next step is when this is done, the next day when you open it, so this is the point where we have done the planning, you can see in the app itself, well, now we have a more narrow window. So what we deliver here is between 18:15 and 19:10. So it is the 20-minute narrow window. And here, the next step, and this is something where we actually work together with customers in a pretty close way, we want to actually notify the customer, and we want to make we want to embed the customer in the delivery journey. So the first step is, well, you just send them a push notification. No real magic about it, but that is something where actually the customer, where you say the customer, we're on the road. And the step that we take here is that we actually make him part of the journey. And part of the journey means that in an Uber-like way, we actually show where we are. And that means that now Marco is on the road and you can actually follow him. So this means the little vehicle is coming along his way. Now currently 5 minutes away from his address, which is Boomberg 4. So this is something where actually customers are opening the app and can in real time follow the drivers. And where we are using here machine learning is actually not so much for the real-time part, but for the route planning itself upfront. So what we do is actually we have so many customers that the routes look nearly every day the same. So therefore, you can train a network and you learn from the best route of yesterday and take it as a base version for today, and then you optimize it again for the next day. And when we are there, we have a simple small sign. So the really interesting part here is, so this is something kind of a gamification feature. Looks funny, it looks cool. But in essence, it helps us also for distribution. Because obviously, if everybody knows when you're there, then you certainly are a little bit more supportive in the process. So that is something which is a kind of a pretty interesting insight. Yes?
Do you show the route that the car is exactly driving? because then I can see which of my neighbors is also
So,
buying.
yeah, that is a very, very important point from a privacy angle. So what we do here is we are actually doing an obfuscation. So what you won't see any other stop along the route that we are taking. And there's even a little bit more. You will not see that somebody will stop at the previous customer. So there will be a linear interpolation between the starting point from a hub, so this is the kind of the location where you start in the city, up to your house. Because obviously you don't want to get in this space as somebody that you expose data, other customer data. So that's a pretty important aspect. Good question. So third challenge is something what we did in a kind of a hackathon recently, and that is something what we call the interface challenge. And the interface challenge is for us that we yes.
Maybe still a question about other things. So do you take into account that some customers you have to travel to the back door and that takes more time? Do you do it on a customer basis, or is it still like an average for all customers?
I'm not.
So some customers you have to travel like upper flat, 2 steps upwards, and some customers go at the door in 10 seconds. Do you take that per customer into account? Or
Absolutely. Absolutely. We take this into account. So there are two angles how we take this into account. Number one is, first of all, when we know that he's living on the second or third floor, then we take this into account in the pre-planning. So this is one important aspect. But the other, on which floor he's living?
Yeah.
Well, this is something. Number one is you have some registration data where you can actually get this. But the even more interesting part is, if you have been at your house before, we know roughly how long it took the last time. So that is the kind of the input for the next one, for the next delivery. So then we can pretty precisely actually predict this. So for the interface challenge, this is the last one I want to show. We have been looking into how can we go beyond actually mobile shopping. So our initial decision was, well, or the question that we had in the beginning, do we actually build a website or do we just mobile shopping? And that was something where we had a pretty, let's say, long discussion in 2013, 2014, where it was not really clear. Everybody was saying, well, e-commerce is moving mobile, but actually the bigger piece is still on the web. So therefore, it was not really exactly clear if it's a good decision to go just for mobile. But we made a kind of a bold shot and said, well, we believe in the mobile trend and we just do it mobile. There's no web available. And then now we are going in a step further. And a step further means what comes after mobile. Everybody has a mobile, but the question is, nobody had actually smartphones 10 years back, or it just was starting to become a kind of an important thing. Will we all have smartphones in 10 years' time? Or what will be the next thing?
Fridges, smart fridges.
Smart fridges, Alexa, a lot of stuff is currently. Nobody knows exactly. But one thing what we looked into is, obviously, what is a little bit inconvenient is that you have to take a physical device into your hand and you need to find the product and tap the device, etc. The moment when you actually run low on a product is the moment when you're preparing food. You're preparing food and you're running low on butter or on cheese, on etc. So that is the moment where you actually would like to notify your favorite retailer that you want to have the next time actually some butter, some milk, some cheese, some sausage, etc. So what we thought is, well, maybe we should actually build a prototype with Alexa, and that is something what we have done. I want to show you a little bit how this looks like in practice. So you will see now one of our developers, Lorena.
Okay, I'm going to briefly show you what our prototype for the picnic skill does. And we're going to add some groceries to our basket.
Oh shit.
For example, Alexa, ask picnic to add banana.
Huh? Oh. No. Okay. Let's try it once more. Can you help me maybe?
Yeah, sure. Yes, where's your speaker? There?
I think it's here.
Okay, I'm going to briefly show you what our prototype for the picnic skill does. And we're going to add some groceries to our basket. For example, Alexa, ask picnic to add banana. Okay, I have added bananas to your picnic basket. And then we go check on our basket and the banana is there. we can also say, Alexa, ask Picnic to add coffee. Okay, I have added coffee to your picnic basket, and it is also there. So we can ask, Alexa, ask Picnic what's in my cart. Currently, your cart has 2 articles worth 9.38 euros. Okay, and then we also introduced some speech sounds, which are phrases that Alexa say more expressively. So, for example, Alexa, ask Picnic to add broccoli. Yuck! I mean, I have added broccoli to your picnic basket. Then we can just ask one more time. Alexa, ask Picnic what's in my cart. Currently, your cart has 3 articles worth 11.13 euros. Okay, this is the demo. We will submit this skill for certification later this year, so all of our customers can have it available.
Good. So that was a little bit, this was our prototype that we did with Alexa. Just in the last dinner with Werner, he was mentioning that Alexa won't be too soon in Netherlands, so we will see when we can make it available. But at least this is something what we have been doing, and we are also looking quite a bit in other prototypes, especially on the blockchain side, which is now something becoming a more and more important topic on for all kind of supply chain operation. So I want to close with a couple of learnings that we had during this kind of journey, and that is something what I hope also encourages you a little bit in the stuff that you are doing day by day. So one thing what we learned is that certainly you need to always get started small, but the most important thing is you need to have a kind of a big dream. You need to start and aim for something really significant, because that is the only way how you can really go forward. The second thing is everybody is talking about data, but you will have never enough data. Never. Simple as that. Everybody talks about collecting data, etc., but you won't. So therefore, complement the data that you have with a mission, with an insight, or with anything what you believe in that your software, your product can and should do. Third one, when you're cutting with AI is a great tool, but first do your homework on the data science side. This is a very, very important learning. If you don't understand what you can use, or where you have enough data, where you have respective also good data, clean data, which you learn from the data science side, AI will not bring you anything. Fourth one, very simple one, launch first, and then later think about scaling. Everybody will talk about how do we do this if you're 10 times bigger, 100 times bigger, 1,000 times bigger. But if you don't get started, nothing will happen. So launch first. Very important quote from Reid Hoffman. If you are not embarrassed by the first version of your product, you have launched too late. Fifth one, very important thing. Everybody complains and needs more developers. I would have loved to have more. But the most important thing is great products come from small teams. Don't be embarrassed that your team is too small. Deadlines are always very, very challenging. But the most important thing is you can do great stuff with small teams. Embrace just the resource limitations that you have in your day-by-day projects. So that is the last thing that I wanted to share. Thanks for your attention. Yes. Yeah, somebody.
You asked Alexa to add coffee. Which coffee does it add?
Yeah, it's a very, very good question. So obviously, what the challenge of a voice interface is that offering options, like you have in a visual interface, is a much harder thing. So what we do now here is a very, very simple algorithm. So what we do is we simply execute a search for a term that you want to add, and we just add the first item. So which means it's the most likely to buy item. It's maybe not exactly what you're looking for, but that is a pretty good guess because we are working. Sorry?
Based on your own shopping cart.
No, based in essence, like you would do a search in the store, in your own store. So we have 100,000 customers, and in essence, the personalization makes this 100,000 customer, let's say, the 100,000 customers to 100,000 stores. And the kind of the search that we execute, in the first result we add, we use the product to add it to your basket.
Why not personalized? Like
Yeah.
No, this is personalized because this is actually the first let's say, result for you.
Right.
So that is a pretty good match, but obviously that means you're getting a kind of a self-fulfilling prophecy. You always buy bio bananas, you're asking for a banana, and you get again a bio banana.
Yeah.
So that is likely, this is the most likely item, but maybe you want to go for another banana at some point.
There you get your mom up.
Yes.
You mentioned that the first thing is launching and then it's scaling, right?
Yeah.
And now, again, DigitalOcean. Can you help us? Can you
Sure.
give us a hint of how are you already challenged by your scaling problem, and how are you tackling this challenge? With
If you're not challenged by what you're doing, you're not working on something challenging enough. It's very simple, or you're not growing fast enough. But the main thing is, we got started, well, we are completely AWS based. So we have everything on AWS, and we are using more or less the entire stack there. So that means normal EC2 instances, but then also S3 and all the entire stack that is available here. Databases, we have Mongo as a kind of document database, and then we use Redshift as a relational database. But that's a pretty straightforward setup. No, Kubernetes, now they have now the EKS setup. We have actually our own deployment of Kubernetes, because this is just launched since in November. So we have deployed this ourselves. And that is then used as a kind of messaging queue system, RabbitMQ, Elasticsearch for search. I guess pretty similar to what you guys are also using. Yeah.
Okay. Well,
Okay.
I suppose you had experience with recipe-based shopping. When you order by recipe,
Yeah.
how would you compare the business outcome with this approach?
Could you repeat the question?
Yes. So the question was, do we support, or what is my view on, or our view on recipe-based shopping? And recipe-based means, in essence, that you offer kind of the ingredients of a recipe as a one-click, let's say, add to basket functionality. So this is something which we have been also looking into. The main question is, how do you maintain recipes? And there are, in essence, two ways how you can handle this. Number one is you have it in your own app. Then you have an own team that is maintaining this. That is one possibility. We have done this for some time, but that is something where we need to decide on how we continue exactly. But the even more interesting, let's say, approach is that you integrate in third-party sites. So there's a lot of recipe shopping sites available, and then you link from a recipe site and allow to add all the products to your basket. But this is not so simple, because obviously none of the recipe sites use exactly the terminology that you use on your site. So that is just a kind of a challenge. But join me if you are interested in this topic. Yes.
So do you handle the delivery of products with short expiration date, like banana in this case?
Yeah.
Is there
Okay, let me just, so how do we handle products with a short expiration date? Or in essence, how do we handle perishable goods which are maybe close to the best before date?
yeah,
Roughly like that.
maybe I order a banana and I
Yeah.
receive a black banana. I don't know.
The challenge is going even a little bit further. If you have a brick and mortar store, you go to the store and you decide which product you pick, kind of a fresh product. And usually you pick the product which has the longest best before date. Now, if you do online shopping for food, then actually somebody else does the picking for you. So therefore, there are kind of two challenges. Number one, you need to make sure that you're always picking the best possible quality. So at least on the level where the customer would expect it. So that's a pretty challenging one already. And the second one is, you deliver to a customer, but you don't know exactly when he consumes it. If you go to a normal store, you can actually decide that you buy a product which is just valid for another day or 2 days. But this is in online shopping not good enough. So what we do is we have a best before guarantee. So which means that we actually ship products to customers where the best before date is at least 3 days, or at least 5 days, or at least 7 days in the future. So that is something which is pretty important also to get the trust from customers. Yes.
What is conversion rate for your site?
Conversion rate is actually is a concept which is a little bit harder to define in mobile shopping compared to web shopping. It depends a little bit on the conversion on which kind of sites. So what we have a couple of interesting features in the app itself. So you have a kind of category shopping, and you can add products directly from the category to your basket. Most kind of more traditional e-commerce sites, you need to go to a detail page, so product detail page, and you add this from the detail page to the basket. So therefore, conversion rate is much harder to define here, because on a kind of a category page, so 2/3 of our customers are adding just from the category pages. On this level, you're showing definitely more products that the customer wants. So therefore, conversion rate is not very expressive. But what we know is that a customer will simply convert of every page at least 2 or 3 on every kind of a category, at least 2 or 3 items. So that's something what we can say for sure.
Okay, and the drop rate then could be?
A drop rate means again
On the
taking out of the basket.
So when the customer added all the items into the basket, what is the drop rate from the basket?
The drop rate meaning is that he's not checking it out.
Yes.
That is super small. So I can't tell you the exact number, but if somebody is filling a basket, then the conversion rate is extremely high. So the conversion in the sense of that he goes to checkout and pays. The biggest hassle in such a business is still actually to make the conversion seamless, easy. Payment is the biggest challenge for all kind of mobile shops. You need to go to Ideal, and if you don't have the Ideal app, then you end up on a website and all kind of stuff. So that's the biggest hurdle that you have in such a business. Now Apple Pay is since a couple of days also available in Netherlands, so we will see how this will continue.
One last question.
I've seen many more questions. Yeah.
So the delivery is free, right?
Yeah.
So how, I don't know, I never used it. How are you actually making profit from it? Are you increasing the price of the product or any other stuff?
Shops that are asking for delivery fees are not asking for delivery fees to make money, but just to finance an inefficient distribution. So the starting point is very simple. If you think about the distribution model, that is a little bit smarter, a little bit more efficient than everybody else in the market is doing it, then you simply don't have to ask for it. And that is something which you have seen also in other industries. Until 2005, everybody who tried to do fashion was actually not succeeding in e-commerce. And then a couple of people in US, Zappos, in Europe, Zalando, and a few more, have started to say, well, we cannot ask the customer for paying for the delivery. If you buy now something online fashion and you don't pay for it. And even further, you don't pay for the return. And that was breaking up the entire fashion industry. And now we have more than 30% of fashion is actually done online, which is actually a pretty tough industry if you think about it. It needs to fit, it needs to properly look, and all kind of stuff, which is a pretty tough requirement.
But does it imply that the cost of delivery is well comparable to cost of operating the brick and mortar store? Because I think the question was implying that you compare the brick and mortar when people are you have queues to the cash register and
we are not competing with a brick and mortar directly. So in essence, if there's a competition, then it's only about alternative online offers. We are in a business here where still 98.5% of all food retail is done offline, where we are not active. In the areas where we are active, it's less, but actually most people have been going for a long time to brick and mortar stores. So therefore, our competition, the only real competition that you have in such a business, is the habit of people. This means if you're going for 10, 15 years, 2 or 3 times per week to a supermarket, then actually you will do this, if you don't break the habit, for another 10 years. So the real competition comes only from actually breaking this kind of habit and to convince people to do online shopping.
I'm going to jump in, because otherwise, Are you hanging around for pizzas?
Sure.
Okay, cool. So, yeah, you're going to hang around for pizzas. So if anyone's got any more questions, which by those things people do, yeah, feel free to talk through pizzas. I have pizzas, and they've been there for a little while. My coat is keeping them warm. I put, so hopefully they're still warm. If they're not warm, we can nuke them in microwaves. That might take a while. But We'll figure it out. Yes, if everyone could stack their chairs in that direction, everyone has lots of space to like chat and drink beer and stuff. We'll get some tables out, and then yes, I'll see you next month.